Hi everyone, welcome to STS webinar. I'm Jenny, the STS marketing manager, also the organizer of this webinar. Thank you so much for joining us, particularly at this busy time of the end of year. We really appreciate it. For today's webinar, we will involve STS President Alice, Vice President of Strategy Development Frederick, and Technical Director Adrian. Adrian won't present, but he will join us in the Q&A. Alice will bring you some update on STS, and Frederick will share his minds on the wafer supply chain and its impact on the modules. A kind reminder, you can select the Q&A button on the right side of the screen, and welcome to type your questions in the compose box anytime if you have. I hope that you will enjoy the discussion as I will. So let's welcome Alice.
All right, thank you, Jenny, and welcome to this first webinar of STS. Thanks for tuning in. Over the past years, we had quite a number of questions from many clients, and we thought that there would be a good opportunity for us to share all our thoughts and recommendations to a broader audience, and tackling all those discussions that everybody in the solar and storage industry are asking. So today we'll start with touching a very critical topic that is affecting many of you who are developing solar projects, and that's going to be the wafer supply chain along with large PV modules. So Frederick, who is our VP of Strategic Development, as Jenny just said, we'll elaborate on how the supply chain of solar wafers has transformed over the years, and this is going to, and how this is affecting the economic model for the PV modules. And that's going to be a very good background to go to another topic, which is larger modules, a very recent trend in this year once again. Frederick has authored a technical memo for us that we published in October, and that is entitled 500 watt plus watt peak modules, a new generation, and on which we are expressing many of our concerns and inputs. So as Jenny said, we'll have a quick Q&A session, and we'll be happy to answer any of your questions that we'll try to capture. But before that, I'd like to give you a few updates on what we've been up to. So in fact, over the past several years, STS has quite transformed and we have reshaped the company to allow growth and diversification of our business. We've got a lot of inputs from our clients that we had to do more of the work we were doing on PV modules. So for those who are familiar with us, and well, you're quite a number who have followed us for quite many years, you know that the team has grown in size and in competencies. So today we are 3 people leading STS. So together with myself, we have Thibault Lemoine, who is leading our global operations, and Frederick, who is looking after the business part of STS. But behind us, we have a very strong team. Especially, we have a very strong team in operations to develop new services with Simon, to execute the services with Adrien, who will be speaking a little bit later today, and to maintain the compliance of our management system, among a few things, compliance, safety. We have Derry here in Shanghai, who is helping us. You know that impartiality is key to the job we do. So, of course, with this transformation, we've also grown geographically, and especially you'll see that we are right now present in a number of geographies. Especially, we have a very strong and growing foothold in Asia with inspection teams, not just in China, but now also in Southeast Asia. And we have representations on many important markets and we're trying to approach more and more of the countries where our customers are located. The change is also happening behind the scene, and gradually I think our clients start to see the new services that STS are bringing. So from PV modules, we are bringing new services to other components of the value chain in solar. But also now we are entering the energy storage field. So you know that STS is a TIC company, a testing, inspection, and certification company. And we also have a very strong part of our work that is supporting our customers throughout the process, throughout the procurement process, to make sure that they are all set, and that the risks that we know, that we see at the factory every day, can be addressed and reduced for customers when they place orders. So we've increased this, we strengthened the portfolio of services, and we've developed it into new areas. Recently, we've completed a few projects. You can see a few of them now on inverters and on energy storage. We've got some exciting project going on. It's not just a few days at the factory, but we are talking about months-long presence at the factories, whether we are following up R&D projects, product being developed, or whether we are really tackling more acceptance testing at the factories before shipment. And some of them happening at the power plant as well. So really you will start seeing STS present at many areas of the procurement and of the procurement and the lifetime of the power plants. So now you've all tuned in to hear our inputs on large wafers and large PV modules. So I'll give the floor to Frédéric, who is going to address those topics. Thank you.
Thank you, Alex. Welcome everybody. It's really an honor to be representing STS here and now. I'm impressed by the excellent portfolio of client and customers that we have. I think it's really a great chance that STS has to have such a loyal clients, and I'm really, I joined the team about 6 months ago, and I've enjoyed working with you guys, and I really looking forward for even more interaction. Yeah, we decided to start this. It's actually the first customer exclusive webinar that STS is doing, I believe. We decided to talk about something which is at the same time very pertinent, very relevant. Pertinence is, by the way, a core value of STS, and at the same time, it's a story that has been here forever. The impact of wafers and very upstream supply chain on PV has really been a long story. So let's try to dive into that, and you know, my presentation is in 3 parts. First one, I actually want to try to capture your attention by trying to find something that maybe not all of you know in silicon, although you've been in the field for a long time, for a lot of you. So I'm going to try and take the challenge to tell you something you don't know. Then we're going to look at the historical trends of silicon for PV, and then we're going to look at the most recent trend that Alex touched a little bit upon. But first, why is silicon such a great material for PV? Well, first of all, silicon is one of the most abundant. It's actually the second most abundant element on Earth. So I guess you know, some people in the audience will know that. It's still quite surprising to me that almost 30%, so almost a third of the Earth's crust is made of silicon. So we can install and go ahead, guys, install as much as many megawatts as you want, or gigawatts as you want. We will never run out of silicon. And actually, even if the world the Earth runs out of silicon, silicon actually happens to be also the 7th most abundant element in the universe. So even if we run out of silicon on Earth because of PV, we will always be able to find some in the universe. As a matter of fact, cosmic abundance is usually cited in terms of number of atoms of the particular element per millions of atoms of silicon. That's just to give you the idea of how abundant silicon is in the universe. Another remarkable characteristic of silicon is that it is remarkably good material for PV. So the first graph that you see on your right-hand side is the solar efficiency as a function of the band gap of the semiconductor. So silicon is a semiconductor. You need a semiconductor to make a solar cell, and the semiconductor is defined by a band gap, and you see that the band gap of silicon at 1.1 is actually not too far from the optimal of this curve. It's not quite there, but it's pretty close. So it's already a very good material for making a single junction PV components. What is more surprising maybe is that if you look at tandem cells, so tandem cells are two different band gaps stacked on top of each other to increase the efficiency that you can collect. And theoretically, you can go to efficiency exceeding 45%. And again, theoretically, if you look at the efficiency that you can get as a function of the two different band gaps that this tandem cell would be composed of, you have the top cell on the y-axis, and then you have the bottom cell on the x-axis, and you realize that the purple local maxima is actually on the 1.1 EV line. So silicon is actually an excellent semiconductor also for two band gap, and that is one of the reasons why there is a lot of talks on tandem cells, basically mostly with the perovskite type of top cell. And there is, as we speak, a company, Oxford PV, which is building a tens of million dollar facility in Europe right now for 120, more than 100 megawatt per year production capacity of perovskite on silicon tandem cell, which is, I think, quite remarkable. And then if you were not convinced that silicon was really an incredible material for PV, when it is time and when we want to go to 3-junction to go even further in terms of efficiency, well, guess what? Silicon is still an optimal material, this time for the median band gap. You see that 1.1 is very close to the optimal band gap for 3-junction. Okay, so that was a short introduction on silicon. Let's have a look now a little bit in the past, and let's see the historical trends of silicon for PV. And I want to start with actually the price of polysilicon because this story is quite interesting. So the price of polysilicon, when you look at it, you monitor it since the 1970s until today, you realize that during the first 2 decades, it was following a cycle, and the cycle is actually well known from economists. It's a cycle from some community that make time to mature, and typically they refer to this type of cycle as the pork cycles. Basically, you have some demand to more pork or cattle, and then the prices go up. So you end up with having a shortage, and at this moment, everybody thinks, oh wow, it's a good idea to breed porks because the prices are high. So everybody at the same time starts breeding porks, and when a couple of months or years later, all the porks are ready to hit the market, well, everybody is ready at the same time, and the prices collapse. The market is not attractive anymore, so people leave the market again, and then the prices go up again, etc. You have a typical cycle due to the fact that it takes, and polysilicon is the same, it takes quite some time, it takes several years to build a polysilicon factory. So you have these cycles which follow simply the cycle of capacity of the polysilicon. But then what happened? In 2008, as you see, there was a disruption in this cycle. And since then, the prices have been actually below $20 per kilogram, and nowadays, closer to $10 per kilogram, except very recently, actually. So what happened exactly is that, well, before this time, the silicon price was driven mostly by the needs in the microelectronic industry. But in 2004, the European, in particular the German market, completely exploded in PV, creating a surge for demand for PV and therefore polysilicon. And this surge was such that the material that was fabricated for semiconductor was actually not enough to feed the entire PV industry. And then you ended up with prices, spot prices, hitting close to $500 per kilogram. So that was really a very sharp peak. And then everybody at this time thought, okay, well, that's going to be that's a very expensive material. I'm going to build a plant so that I can put this material on the market. So there were a lot of plants that were built. Even module makers went upstream and built their own plant to ensure security of supply, in fact. So from 11 plants in 2004 to 61 in 2010, just to give you an idea. All these plants arrived at maturity at the same time, so you can imagine the PERC cycle took place again, and then the prices completely collapsed in the year 2009-2010. Other venues were tried, such as upgrading metallurgical grade, and there was something also that was called, that was an indicator, a performance indicator. You wanted to have as many watt peak per gram of silicon. So gram of silicon was really a resource that was hard to get, so expensive, and there were wafering techniques, for instance, to reduce the amount of watt peak per gram, for instance. Nowadays, most of those have been abandoned. Most of these ideas have been abandoned because there has been a strong ramp up of polysilicon facilities, especially in China. But this effect was quite strong. It was actually so strong that you see it on the curve, the learning curve, or sometimes it's called the Swanson law, which plots the module price as a function of the cumulative module shipments. So typically, every time you double the cumulative module shipment, you will decrease the price by about 20%. And then you see that there's a bump here on this line, and actually the 20% is a fit. And depending whether you take into account this bump or not, you will have another learning factor. 20%, just to give an idea, it's about 75% price drop every 10 years. It's about, I think the last 10 years, it's been a little bit steeper here. So we have actually dropped a little bit faster. It's more like 90%, in fact, in the last 10 years, and about 10% price drop per year. So a good from a bad, we have actually now our own polysilicon supply, and they are in the recent news. We will see that at the end. There has been a lot of movement on the supply of polysilicon. It is so the metrics of grams of silicon per watt, or watt per grams of silicon, may actually come back because the polysilicon is responsible for 70% of the energy demand of one module. So in markets where the carbon footprint may be an argument, you may have some comeback of these kind of ideas, or at least moving the polysilicon plants to some carbon-free, carbon-neutral, low-carbon energy sources. So that's one trend I wanted to talk to you about. Another one that I wanted to talk to you about, very historical as well, is monocrystalline versus multicrystalline. So monocrystalline actually had a head start, mostly because of its ties with the semiconductor industry. So you see that the light blue was mostly monocrystalline in the 80s, but you see some other trends which are pretty interesting. And in particular, I want to highlight this region of continuous decrease of the market share of multicrystalline, where there were a lot of multicrystalline improvements. Somehow the technology was favorable to the multicrystalline players. For instance, with the apparition of quasi-mono, the apparition of high-performance multi, economies of scale, simply, it was looking as if monocrystalline was going to disappear for PV. But recently, what happens is actually the opposite. There were some large investments from some Chinese company, in particular, including in R&D, and I want to say Longi here in the years 2014 to today, in fact, which have been really boosting the monocrystalline material. And at the same time, as this happened, there has been also some new technologies which have been developed, which happen to be synergetic with monocrystalline. Diamond wire sewing, for instance, one of them which works much better with mono than with multi. And the PERC technology as well. In fact, one of the problem that was found with multicrystalline for PERC, it is possible to do a PERC cell on multicrystalline wafers, but you have what is called LeTID, light and elevated temperature induced degradation, and this new degradation mechanism discovered in something like 2012 is actually much more severe on multi. So that is a boost for mono. And you may say, okay, but mono still has the traditional historical boron oxygen LID issue, which is very pronounced in mono PERC. It's more pronounced than in multi. Yes, that is true. However, there has been some industrial solutions which are now available and that we see in the factories to remove this light-induced degradation phenomenon. LeTID is still not completely known. It has been observed in mono PERC. It has been observed even in float zone wafers. It has been observed even in N-type wafers. But still, when you look at the data, multi is hit harder, and that is a difficulty for multi. Last historic trend that I want to talk to you about is N-type versus P-type, also very, very historic. This time P-type got a head start, and mostly for reasons of better resilience for space application. However, the highest efficiency most of them are done on N-type when you look at what happened. And in fact, today the top efficiency, the record efficiency held by Kaneka is indeed on N-type material. N-type is also free of boron oxygen, and it is even claimed that it's less sensitive to LeTID, but this is still a little bit under discussion. But somehow N-type had up to now some technology barrier that were difficult to overcome. The boron emitter growth or diffusion is a problem with the boron skin. The growth of phosphorus silicon is also an issue. So it is a little bit more difficult to do N-type, and that's one of the reasons why it's not dominating technology today. But it may change. It may change quite fast, actually, because there are a lot of very strong companies which are investing very heavily in N-type. In fact, companies like Jollywood are betting their entire roadmap on the improvement of N-type structures. And there are actually two technologies which are competing. So maybe in a year or two we will be again together, and I will describe the game, the match between TOPCon and heterojunction emitter on N-type wafers. But okay, on to the recent trends, what everybody is talking about today. As Alex introduced that a few at the beginning of this introduction, one of the things which is really a very strong trend in 2020 is the increase in wafer size. So there has been a steady increase of wafer size along the years, but it has been accelerated quite dramatically in the last few months. Today, M6 wafers, 166 millimeter, is most probably the dominating technology in 2020. However, it was not the case in 2019, and it is likely not going to be the case in 2021 because there are a lot of announcements and a lot of investments which are made on two actually competing technologies. One of them is the M10 wafers, which is 182 millimeter, and the other one is the G12, which is 210 actually square wafer. And what is interesting is that there is some kind of I don't know, a match, a war between two gangs or clans that are competing to. They're competing for what? They are simply competing for the domination of the market in the next few years. We know that it's very expensive. It's very expensive to invest to launch a new technology, and if the market adopts one or the other technology, then all the investment that the other group would have done will be relatively obsolete. And that's the case, for instance, for the people who have heavily invested in polysilicon, in multicrystalline silicon. For instance, GCL has a lot of cast multicrystalline silicon, which starts to become obsolete. So it's really fighting for the domination of the market. And both of these groups actually are proposing and claiming that they should take that we as an industry should take their proposed solution as a standard. LONGi first in June 2020, and then recently in November, Shongwan and the group behind actually proposed a standard on 210 millimeter square wafers. So larger wafers trickle into larger cells, which trickle into larger modules, and that's the reason why we see on the market much larger modules. These are all the pictures of the 500 plus. So you realize that I use 500 plus, so higher wattage as similarly to larger modules. In fact, we have not seen any increase in efficiency. The efficiency remains more or less the same. The main difference is in the size of the modules. So we have indeed written a memo, a new generation 500 plus module that you're very welcome to ask us for it. We'll gladly provide you with a copy of it. We don't put it on our website. We want to keep it for our customers. We think it's important that we keep on giving you some insight so that you keep an edge on the market. So that's why we want to share it first with our customers. Let's have a look at a few. I have 3 different slides which show the few risks that we have identified, which are exposed, which are described in this memo. So the first is all the risk associated with processing of larger wafers into cells. The obvious one is most probably the wafer breakage. If you keep the same thickness, even actually go down in thickness to save material and to save costs, down to 160 micrometer, handling larger wafers becomes a challenge. Some of the tools are very advanced to handle large wafers, and it just becomes more and more challenging when the dimension is increased. Another risk is the surface passivation. Most of the new technologies will actually rely on some kind of thin film deposition. PERC, for instance, you have a PECVD thin film on the front as well as on the rear. TOPCon, which is viewed today as what looks the most as a drop-in solution beyond PERC, relies on a tunnel oxide which is only a few nanometers thick. So very thin layers. Heterojunction, the same. They rely on tunnel tunnel transfer of electrons to the electrodes, and that is a very thin layer. So if it's thin, and if you miss the thickness by a few nanometers only, then you may run into problem. So homogeneity of the surface passivation is an increasingly critical step. And when you go larger in size, the larger you are, the more difficult it is to be homogeneous. There is a reason why Sanyo Panasonic cell dimension have not gone above 130 millimeter. Now, if you look at the next step, so from cells into modules, you see that well, when you're bringing more cells, larger cells, you run into a problem. You absolutely don't want to increase the voltage. Actually, most of the new modules have, if anything, a lower voltage than the traditional ones, because you want to put as many modules on one module string as possible to reduce the balance of system costs. But then okay, if you increase the wattage and you cannot increase the voltage, then you have somehow to increase the current, and that is exactly what a larger cell does. So you have to have ways to mitigate the increase of currents coming from the cells. And that comes from cutting the cells, sometimes in 2, sometimes in 3. That comes also from increasing the number of ribbons, finding other ways to interconnect, like for instance, shingling or partial shingling, tiling ribbons, seamless soldering. Basically, every big brand has its own way of doing interconnection that will reduce the series resistance and therefore the impact of larger currents. That is the goal of all most, if not all, of this technology. So we have actually an addendum in the STS standard, which is addressing exactly the problems that you may have with laser cut cells and with multi-bus bar. And then another one that I want to point to your attention is the final quality check. So the sun simulators are expensive pieces of equipment, and they don't prevent you, if you don't have the latest quality or the latest tool, it does not prevent you from producing and therefore selling modules. So it's not a blocking factor in the factory. However, it is a critical one if you want to have accurate understanding of what you are buying or selling. And in fact, a pattern simulator typically are tunnels, which are very long. And why are they so long? Why is it 8 meters long? Well, it's because you want the light to be as collimated as possible when it reaches the modules. And that comes only with, I mean, you could imagine some very complex ways with lenses, but the dimensions are just too big to do something like that. So you see that there is a problem of dimension, of macroscopic dimension, which is coming up. And this is something that really people should pay attention when they are qualifying a factory or qualifying a lab. And now moving on to larger modules in general, there are a couple of questions that people ask themselves. Do larger modules run hotter? If you have higher currents, it would be natural to expect that. However, with what they call the twin modules, where you have a higher number of strings which are only recombined at the combiner box, you may control the current. There are ways to limit the current into the module. But still, it is a point of attention. We can be careful with that, especially because a higher temperature of operation will also increase your degradation rate. I think the rule of thumb is something like a 10-degree difference in operation will increase your degradation rate by a factor of 2. So it's significant. Then a lot of people are also talking about the logistics. Larger wafers are how many can you fit in a standard container? How many people do you need as an EPC to put the modules together? Actually, this is one of the arguments from the M10 team to try to push their standard. They say that the logistic will not work for G12, and you have to stay reasonable and go to M10. It's one of the reasons. And indeed, there has been a lot of there is certainly some value in these larger modules. But a lot of the risk have been pushed actually to the EPCs and to the developers, as you can see in these three examples. The third one was actually weather susceptibility, another maybe obvious one. If you're reducing the thickness of the glass and of the frame and having larger form factors, you are more susceptible to breakage in the field. Last but not least, I want to point your attention to something which is very hot right now in the US, maybe a little bit less in your country if you're not dealing with US projects. But there has been a law, an act passed by the House in September, Uyghur Forced Labor Prevention Act, that prohibits the import from the Xinjiang province, and the Xinjiang province happens to be host of about 1/3 of the capacity of polysilicon in the world. So this is something that STS is looking very carefully into. We are looking at ways to control and trace the supply chain, making sure that your suppliers have the right supply chain in place, that they can control exactly where their raw material is coming from, so that when they need to ship to the US and maybe to other regions in the future, they can demonstrate that there is no forced labor involved. In fact, I believe that polysilicon supply chain is going to be essential in 2021. And I want to finish with that. There has been indeed a lot of movement in the wafer supply chain. Just very recently, in the last 3 weeks, Ryzen Energy enters polysilicon production. GYT Corporation, which is a PV equipment, is building a silicon ingot manufacturing, 24 gigawatt. Jinko partners with Tongwei. Trina partners with Zhonghuan. Trina partners also with Daco, actually. So there has been a lot of announcements, a little bit like if the entire supply chain was preparing for a disruption very much upstream. So that is really something to keep an eye on, and I invite you to do so, and we're welcoming any question or any solution that we can bring to you for that. As my summary, silicon, just to go over what we talked about briefly, silicon is actually an exceptional material for PV. Sometimes we don't realize how lucky we are to have this material for PV. Since the 2070s, there has been many variations of silicon PV, and there has been also a number of historical matches, games between, let's say, mono and multi, P-type and N-type. Maybe the next one is TOPCon versus heterojunction. And the next one is obviously M10 versus G12. And today, the material, the upstream part of the supply chain, remains really at the forefront of the relevance for everybody working in the PV markets. So with that, I would like to thank you for your attention, and we are now opening the Q&A session.
Thank you. Thank you, Frederick. Sorry, the network is a little bit down here. Thank you for your great sharing. I really can't wait to enter into the Q&A session, because here I can see that we have got some really great questions. So here I see that we have the question. It is about the large wafer manufacturing. The question is, do you see already a lot of large wafers in manufacturing? Adrian, you take charge of the project management in STS. I think you maybe have something to share on this.
Okay, first, hello everyone. Regarding the question, I would say no. Currently, the largest wafer size we have seen in factory during our inspection is 166 millimeter. So if we speak about the next generation that have been introduced by Frederick, like M10 or G12 design, currently it's mostly seen on data sheets, on prototypes, but not yet in mass production. However, we have seen some trend, and based on the latest feedback we got from some tier 1 manufacturers, we would expect to see some mass production ramp up for large module happening during Q1 of next year, so very soon.
Okay, thank you. Thank you, Adrian. I see, thank you. Okay, I see we have another question here, and the question is, for perovskite solar cell lifetime is major concern. What are the measures taken to overcome from this, and what is the current lifetime of cell made? So I think this one, maybe Frederick, can you answer on this one? Do you have something to share with us?
Yeah, thank you. It's a good question. Indeed, there are two issues with perovskite. One of them is a contamination, potential contamination, and the other one is the lifetime. Perovskite is actually a salt, so it will dissolve in water, which is pretty inconvenient. So actually, that's, silicon is not, and it will not dissolve in water. It's very difficult to oxidize. Actually, to oxidize more than a few nanometers. Few nanometers oxidizes very fast, but then it stops. So perovskite is difficult to make last longer. And I don't know all the secrets of Oxford PV, but last time I had the chance to talk to their CEO, it was about a year ago, and I tried to understand where they were standing, and their answers were, well, you have two different types of lifetimes. You have the lifetime of the cells which are encapsulated, and they were talking about months, not years, but months. And you have the lifetime of the cell before it is encapsulated. So basically, at the moment you're fabricating it, you need to put them as fast as possible into the encapsulation so that it's protected from moisture. And this was in the order of weeks, according to Oxford PV. So yeah, that's what I can bring to this discussion.
Thank you, Frederick. Very insightful for us. Okay, here I can see another question. It is about the question is how module manufacturing will assure their customers for LeTID problem in PERC modules. So, Frederick, Adrian, or Alice, which one of you would like to share something on this?
But I'm okay to I'm happy to answer this one. We have we have this question all the time. There is we very regularly do LeTID testing on a lot by lot basis. We do recommend that because LeTID is a question of material, of silicon material. Well, it's not completely understood exactly what the phenomenon is. It's the most acknowledged explanation is about the presence of hydrogen and the state of hydrogen in the material. But yeah, and that is why we recommend to do it on very regular basis. Just having one test results from the manufacturer showing that they have no LeTID problem, that it's not sufficient, because the very likely the lot of your wafers and your cells and your modules will be different from the one that was tested. So we do recommend LeTID testing on a lot per lot basis.
Yeah, I fully agree with you, Frederick, on that. I think module manufacturers are not going to have an easy time assuring their customers that the product they can provide are free from LeTID, and One of the essential points here is indeed the value chain. Frederic, you gave earlier some examples of module makers making deals with cell suppliers. And while we know that module makers are using multiple cell suppliers, and how to consistently ensure that every supplier has on a regular basis tested their solar cells for LeTID, this is not something that the suppliers are going to follow through very carefully enough. So I don't think there is a strong assurance that can be brought by the manufacturer, and on which we can actually vet that the process has been thoroughly brought through. So key point is continue monitoring on your order that those batches are LeTID free. Reduce the number of solar cells that are being used on your order so that at least you reduce this risk exposure as well.
Okay, thank you. Thank you, Alice, for your opinions on this. Really informative and insightful. And okay, I also got another question. It is also about the larger module. The question is, why do you think this chain of larger module happens so subtly? I think this goes back also to Alex. So
yeah, I'll be happy to answer on this one.
Okay.
Well, historically in this industry, manufacturers have guided how the supply chain should change. It's not really driven by a customer demand, but more by a cost per watt peak opportunity. So if you look back, for example, in 2007, when the value chain changed from mono ingots to multi ingots and wafers, that was due to the fact that silicon was, we could use more reclaimable and cheaper silicon materials to produce multicrystalline silicon wafers, therefore reducing the cost per watt peak, while the demand could accept any price, and same as monocrystalline price. So big players like LDK shifted, they really led the industry to shift towards multicrystalline. I think here we are in a similar configuration. Module manufacturers have recognized that there is a gain to manufacture PV modules with higher wattage. This, I think Frederic mentioned that very clearly. There's no gain in efficiency, at least that's not the main driver. But if on the same module, you can increase the wattage, you will reduce cost a little bit on the raw materials, but also on the processing cost itself, on the manufacturing cost itself. So for the same piece, you probably have to spend the same power, the same very similar processing time to manufacture a module, and you'll get some gains in that area as well. Not to mention the logistic costs that can be reduced further. But one thing that we'd like to highlight is the fact that many of those technologies are new. They are not tested thoroughly enough. They are brought to the customers, and customers are exposed to the risks. Sometimes the technology is not vetted enough. So breakage on site, hotspots, really quite a number of issues that manufacturers would have to, that customers would have to face. So early adoption might not be the right approach. We still recommend that you get third-party extended reliability test report to see how the technology performs in harsher conditions. When you don't have that available, we also have some solutions to go and audit how the supplier did its R&D. That's what we're bringing right now to our customers. We want to see how the supplier developed its product. Did they follow a thorough process? And what were the results? We're going to analyze that. So, yeah, be careful with these new technologies. There is a strong drive from manufacturers, but it can be to the detriment of you guys buyers.
Okay, thank you, Alex. I can see we have another question here. It is actually about the glass and frames. Is the downward trend on glass and frames dimensions continuing? Adrian, you want to take this too?
Sure, yeah, I can take this question. So indeed, we have seen a trend during the past couple of years of decreasing thickness for both glass and frame. If we separate the two components, speaking first about the glass, so far we don't see any trend to increase the glass thickness. So we estimate it has reached its stable conditions. Despite some issues, some issue on the PV systems, some failure, especially due to hailstones in areas such as Texas in the US. Regarding the frame, it's a different story. To illustrate what Alex has just described, we have seen last year some projects on which a frame thickness reached a lowest of 25 millimeter. And so far this year, we have not seen such products, even on glass modules, as the lowest frame thickness this year was at 30 millimeters. So this might be a hint that a lowest has been reached last year, and that we have to be very careful on what are the design proposed by the manufacturers, as some tests might not be successful.
Thank you, Adrian. Thank you for your information on this. Okay, I can see we have another question coming in, and this question, let's see, it is also about the large wafer and module, I think, and I think it is more about STS expertise in the question is, what is STS doing to reduce risk related to large wafers and panels? So, Alex or Adrian, which one of you want to answer this? I think maybe Adrian will have more to say on this question.
Sure, yeah, I can start on this one. So we are acting at a different level. We can first speak about the product design. We have to ensure about the compatibility of the modules with the mounting structure. So we would recommend to validate this first step by getting some result of either static or dynamic mechanical load tests that are performed on modules, preferably at third-party laboratories and before the mass production starts. In terms of inspection done during the production, so far we apply our STS standards, and we found that some of them were very pertinent for these new designs. For example, the bending performance of the glass that we measure during the incoming quality control, and it's something that will show to be useful for, especially useful for this new design of modules. During the manufacturing process control, we have also strict criteria to monitor the stringing laminations and that are suitable for those new designs. In terms of pre-shipment inspections, we have kept the same criteria than the current design of modules, and we have to be especially careful on the EL images analysis, especially for the micro crack of the cells, as well as the dark edge on the cells that have been described previously by in Frederick's presentations. And for this part, yes, we consider that our standards are suitable for those new designs in order to limit the risk of performance degradation once the module will be installed in the field.
Okay, thank you, Adrian. Very thank you. Also, okay, I see another question coming in, and I think maybe we will be the last question about this webinar. The question, I think the question is for Alex, because, and I think it will also interest others under this special coronavirus situation this year. So the question we get here is the coronavirus situation still affecting the supply chain today. Alice, because you know quite well about the Chinese period components manufacturing in China. So I believe that you maybe have a lot to say on this topic.
Yes, we are following that closely, of course. COVID-19 had an important impact on the value chain, not just at the moment of the outbreak, not just after the factories started to regain their manpower and their raw materials, but even after that. We've seen, I think as recently as last month, one of the major module maker failing 3 times in a row PID. Why are they still failing PID? I think the solar industry has resumed in Q3 very fast, and factories are ramping up. They are bringing new production lines into operations, but the lack of manpower that are qualified. I think earlier this week we had another audit at one of the major guys at a new factory, and many of the workers are not that qualified. We see that the same thing is happening upstream to the component makers. They are facing the same situations, the same issues, the same challenges. Their operators are not that qualified, and they have to produce. So they have to get raw material fast to produce, and sometimes the raw material quality itself is not good enough. So there's been quite a lot of loss in the control of the value chain upstream, and we are still seeing the impact right now. So it's still going to take some time until things stabilize, especially because the industry overall is ramping up very fast.
Yeah, sure. The impact is not easy to go away completely. Yeah, I agree.
Yeah, it's going to take a while.
Yeah, thank you, Alex. Thank you. So time flies. I think we come to the end of this webinar. Thank you everyone for joining us today. We hope that you enjoyed this webinar topics. And if you have any other questions, or if you want a LeTID module memo, welcome to contact us. And it will be also available on our website soon. So thank you very much. See you next webinar. Bye.
Thank you all.
Thank you.